On July 16, 1969, Apollo 11 was launched on a flight to the moon. Another giant step was being taken by the United States in the exploration of outer space.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
All that we have accomplished in space, all that we may accomplish in days and years to come, we stand ready to share for the benefit of all mankind.
As we explore the reaches of space, let us go to the new worlds together, not as new worlds to be conquered, but as a new adventure to be shared.
After a 3-day journey, the goal is reached.
Houston, Tranquility Base here. The Eagle has landed.
And then after a 7-hour rest and preparation period, the historic step is taken.
I'm going to step off the limb now. Small step for man. One giant leap for mankind.
On July 20th, 1969, the first man from Earth set foot upon the moon. And as each further step into space is taken, new frontiers are opened and greater goals are set. Science for the 70s. Space-age challenges to the students of today. Science for the 70s at Western Kentucky University. How is Western meeting the challenges of the space age? Here to tell us is the head of the Department of Physics and Astronomy at Western, Dr. Frank Six.
Since early man walked this young planet, he has speculated about the nature of the universe. Astronomy is the oldest science. It all began with the systematic observations of the Chinese in the 13th century BC. Curiosity, inquiry into the nature of heavenly objects and events brought on the birth of the scientific method. Today, man understands some of the laws by which nature works. In them, there is beauty, simplicity, generality. They are important because they shed light on the conditions and events that brought our world into existence, that brought us into existence, and that will ultimately decide our fate. The program in astronomy at Western Kentucky University exposes students to this rapidly expanding frontier of knowledge. There are courses in general astronomy, which survey the solar and stellar systems. Techniques are taught in observational astronomy, and physical processes examined in introductory astrophysics. There are special courses for teachers and liberal arts majors, as well as an evening course for adults exploring the universe. The faculty actively participates in research. One studies the structure of our galaxy by measuring the emissions from very red stars. 2 professors are investigating atomic collision processes in the upper atmosphere, while 2 others record the long-wave radio signals from the planet Jupiter. To convey the excitement in astronomy, we believe students must be involved. Our facilities were selected with student participation in mind. The 3 major components are a 180-seat planetarium, a rooftop optical observatory, and a radio observatory. The Hardin Planetarium, adjacent to the science complex, is a theater of the sky. Paul Campbell is the assistant director of our planetarium.
While the main objective of the planetarium is educational, the presentations could also be considered entertaining. A sophisticated projector system recreates the heavens with fascinating realism. The programs are spectacular, ranging from the setting of the sun to meteor showers, to constellation figures, and even to the flight of a spacecraft across the sky. Through the movement of the projectors, time is condensed, stopped, and then restarted again. This provides an opportunity to demonstrate over and over again different astronomical occurrences for clarity and understanding. The diurnal movements of the heavens from east to west as a reflection of the Earth's rotation from west to east is clearly demonstrated. We can also show the sky as it would appear from different latitudes. One of the many special effects that is controlled by the instructor at the master control console is a projected luminescent grid system superimposed on the star sphere. This changes the sky into a three-dimensional blackboard on which concepts such as altitude, azimuth, declination, and so on can be demonstrated. One of the primary functions of the planetarium is to meet the needs of the university-level astronomy students. Through the use of the three-dimensional planetarium sky, they are introduced to concepts that would be difficult to explain using any other medium. Various other programs have been designed to meet the needs of different groups within our community. A series of planetarium demonstrations for the teaching of basic astronomical concepts is available to students of all levels, K through 12. In addition, programs are available for interested groups, such as clubs, civic organizations, and other colleges. We also have programs for the general public. These programs are presented on a regularly scheduled basis on Thursdays, Saturdays, and Sundays.
The planetarium is a most versatile facility. It is the ultimate visual aid in that it permits simulation of the heavens as seen from any point on Earth at any time, past or future. Another vital part of our astronomy program is the rooftop observing deck. This optical observatory permits direct examination of celestial bodies. Tony Vavrukevich directs this activity.
Our astronomy program at Western Kentucky University is a well-integrated one. For instance, our observatory is used for elementary research, the teaching of undergraduate students, and as an aid to the planetarium program. An observatory typically consists of a telescope protected by a rotating dome with a movable opening. The dome is basically there to protect the telescope and auxiliary equipment from external elements such as wind and rain. At the same time, the movable opening allows observations to be made without actually removing the dome. Our major telescope, a 12.5-inch Cassegrain reflector, is found within this dome. As this telescope is meant to be used by graduate students in running simple observing programs, a clock drive is required to compensate for the Earth's rotation. The 12-inch also has peripheral use in our planetarium program. After visitors to the planetarium have seen the regular show, they are often taken to the roof to view prominent objects such as a bright planet or the moon through this telescope. 9 smaller 4.25-inch Newtonian reflecting telescopes are of great value in our undergraduate program. Most of our undergraduate students have never been made aware of the many interesting faint and distant objects that are found beyond the solar system. Here at our rooftop observatory, we introduce them to the sphere of stars surrounding us and acquaint them firsthand with the subject matter of astronomy. Western is very fortunate to have a unique astronomy program which moves the student from the classroom to the artificial sky of the planetarium and finally to the real sky of the observatory as seen through the eye of the 4.25-inch telescope.
Although many secrets of the universe are written in light, there are ways of learning about the heavens other than by peering through a telescope. Radio waves from sources deep in space penetrate the Earth's atmosphere and bathe our planet day and night. In 1930, Carl Jansky, an engineer with Bell Labs, detected a strange hissing in his receiver as he scanned the sky with a large antenna, trying to track down sources of radio interference. This was the first time radio signals had been knowingly detected from space. They were coming from the center of our galaxy, the Milky Way. Since World War II, radio astronomers have added enormously to their knowledge by studying the radio emissions from celestial bodies. Western is fortunate to have its own radio observatory, located 12 miles from the campus. We are presently trying to determine the size of the radio sources on the planet Jupiter. A radio telescope consists of 3 major components. The antenna collects the signal of interest. A radio receiver detects and amplifies this signal, and a recorder makes a permanent record available for later analysis. The receivers, recorders, and auxiliary timing equipment are arranged around the observer for easy access. The larger you make the antenna, the more energy you are collecting. This means you can detect weaker sources and also see finer detail. Our experiment requires accurate timing information because we coordinate our data with that collected at observatories in Florida and in Chile. This loop antenna receives a standard time signal from Boulder, Colorado. The large antenna is mounted so that it will turn and counteract the rotation of the Earth. This enables us to track a source as it moves with respect to the ground. As we look at the giant planet, we will hear its sporadic radio emission recorded by an observer on watch. These emissions sound much like static in a radio receiving set. Yet it is impressive to realize that they have traveled to Earth from the planet Jupiter, a distance of over 500 million miles. You have had a brief look at some of the science facilities at Western. Just what is their significance? Should students have an awareness of their place in the universe, of the objects, forces, and events surrounding us in space? I think you will agree with me that the answer is of course. The educated person should know these things. The facilities you have seen make the college professor's job easier and more enjoyable. But most important, they arouse the student and make him ask why. What is the challenge of space? Suppose we take an imaginary journey, starting from some point out in deep space, and travel with the velocity of light. First, from our vantage point, we see numerous indistinct blurs. These are but specks of light in the distance. We are surrounded by emptiness. If we aim for one of these blurs in the center of this square, in about 2 billion years, traveling at the velocity of light, we are close enough to see that it is an island of stars, what astronomers call a spiral galaxy. In the observable part of the universe, there are 1 billion of these star systems. Entering this galaxy, which would take us another couple of million years, we find ourselves in interstellar space. There are stars in all directions, about 100 billion in this particular cluster. Some of the stars are immersed in faint glowing clouds of dust and gas. Aiming for one of these points of light, we find that it is not a point, but a bright disk. The closer we get, the more intense is the heat and light generated by thermonuclear reactions within its hot, luminous sphere. We veer to one side to escape its heat, and 8 minutes later approach a tiny blue and white sphere that we call Earth. Now we have entered planetary space. It looms closer and seems to be about 8,000 miles across. It spins like a top, turning different sides into illumination by the star that almost destroyed us. It is a place of warmth and beauty. There are rushing waves, mountains of molecules, each stupidly minding its own business, trillions apart, yet forming white surf in unison. Ages on ages before any eyes could see, year after year thunderously pounding the shore as now. For whom? For what? On a dead planet with no life to entertain. Never at rest, tortured by energy, wasted prodigiously by the sun, poured into space. Deep in the sea, all molecules repeat the patterns of one, till complex new ones are formed. They make others like themselves, and a new dance starts. Growing in size and complexity, living things, masses of atoms, DNA, protein, dancing a pattern ever more intricate. Out of the cradle onto the dry land, here it is standing, atoms with consciousness, matter with curiosity, stands at the seal, wonders at wondering. I, a universe of atoms. an atom in the universe.